Hello, it's Mr. Claudy, and today we are finally ready to start looking at exponential functions. We've talked about exponents, but now we're actually going to look at that member of the function family, the exponential functions. And I'll start that off with a question. What would you rather win? $1 million now, $1 million today, or 1 cent? Now, you guys don't have pennies anymore, but imagine getting 1 cent and double that every day for 30 days. So on the first day you get 1 cent, the second day you get 2 cents, the third day you get 4 cents, 8 cents, etc. What would you rather have? And I know by looking at this, my instinct is $1 million now, because even if I double 1 cent a bunch of times, I don't think it's ever going to get to be more than $1 million. But let's use math and just double check. So let's say on day 0, so I'm starting off with 1 cent. On day 1, I'm doubling it. So I have 0.01 times 2, which gives me 0.02. On day 2, I have 0.01 times 2, and then I'm multiplying all that by 2. So that gives me 0.04. Okay, on day 3, I have 0.01 times 2 times 2, and now I'm multiplying that by 2, which gives me 8. Should I do this one more time? Day 4, well, by now we kind of see the pattern is I'm multiplying for day 3 0.1 times 2 times 2 times 2 times 2 to the power of 3. So on day 4, I'm multiplying 0.01 times 2 to the power of 4. And I know that this is going to be, I could type that into my calculator, or I know it's going to be 16 cents. So let me fast forward now. I kind of know I have a pattern here, right? I just 2 to the power of the number of days. So let me fast forward to day 30. This is going to be 0.01 times 2 to the 30. I don't know 2 to the 30 off the top of my head, so let me just do my calculator here. So I have 2 to the power of 30 times 0.01, and that gives me 10,737,418.24. Wow. So it appears that you would definitely take the 1 cent doubled each day for 30 days. And we've just witnessed the power of exponential growth, an exponential function. In 30 days, you go from 1 cent to 10 million. In fact, even at day 20, you're still not looking at a lot of money. 2 to the power of 20 times 0.01. Even at day 20, you're only at, well, you're at $10,000. Seems like a lot of money, but you're a long way from $1 million, it seems. But exponential growth, this idea of doubling, moves so quickly that in a few days you balloon up to 10 million. So an exponential function has the form f of x equals a to the x, where a has to be greater than 0. We can't have a negative. A cannot equal 1, and a belongs to the real set of numbers. So just a cannot be 1, because if we know if a is 1, 1 to the power of anything is always 1. So it's not going to be an exponential growth function, and it has to be a real number. You can't have a complex number in here. What does this look like? Well, remember we've already looked at this when we did our function family, but we know an exponential growth function looks like this. My red pen lost. Okay. So we know that the exponential growth function has an asymptote, a line it never crosses, at y equals 0. So as I go, it never actually reaches 0. It gets very, very close. In the positive direction, this is exponential growth. I want you to understand it's not an asymptote because it doesn't approach something. It keeps getting bigger and bigger and bigger, and not quadratic. The quadratic has a very, this pattern of over, up, over, up, over, up. Exponential growth is very, very fast up. So if I were to graph these two, the quadratic would be a lot smoother, the exponential is a lot more. This point here is kind of my only key point. To figure it out, well, this is the point where x equals 0. So I'm going to sub in x equals 0. That gives me, if I sub it into this function here, I have a to the power of 0, which is always 1. So this point is 0, 1. That's a key point on my exponential function. The domain is x belongs to all real numbers. And the range is y has to be greater than 0, but never equal to 0. So that's my exponential function, that's its form, and that's its that's the shape. Exponential functions are something that is really difficult for the human mind to comprehend, to kind of imagine it. As you saw in this question, right? 1 million versus 1 cent doubled each day. You really tend to think of 1 million because it's hard to even comprehend this kind of growth. We don't see it in a lot of places. We see it in population growth, either human or definitely bacteria, nuclear chain reactions, viral videos, compound interest. And the one thing that has made us all very familiar with exponential growth is virus spread. We've all spent a lot of time looking at coronavirus graphs, and we look at how we start off with 1 or 2, then 10, then suddenly we have thousands of people infected with this disease. So virus spread is something, again, it might be hard to imagine that when 8 people have the disease, we could have a disaster that we have today. But exponential growth, it takes off very quickly. So now that we understand the function, we have a bit of an intro to the function. The next thing we're able to do is look at transformations. Let's start with just drawing this function one more time. Y equals a to the power of x. And I'm going to put my asymptote in there. Y equals 0. This is called the exponential growth function. For example, this is when bacteria grows. This is how a bacteria population might take off. Exponential growth, that idea of getting bigger and bigger and bigger. If I were to reflect this in the x-axis, in the y-axis, I end up with, okay, so again, you're going to mirror this the other way around, so now it's going to look like this. And the reflection in the y-axis, if you remember, that means I have to sub in a negative inside my bracket, so I have a to the negative x. Same asymptote. You might hear of this one in science. This is the exponential decay function. Example you've probably heard of. So I would write it y is equal to a to the negative x, or that negative would technically be, because the negative exponent, I could rewrite it like that. Either of these is acceptable, but I want you to understand that the negative here is a reflection of the y-axis. Graphically, I've just flipped it around the y-axis. You see things like this when you look at half-life, which you've probably done in chemistry. That is nuclear decay. right? I have a little bit of plutonium, I let it sit around, it decays at a certain rate, so it divides in half every few days or something like that. And so you see the mass of the plutonium decrease. Never totally disappears though, it reaches an asymptote at y equals 0. The transformations, again, you spent a lot of time working on them, so at this point you should be pretty comfortable with transformations. Let's just go through and look at how my transformations have, which different transformations these are. So if I have a negative in front of the function, that is a reflection up-down, or a reflection in the x-axis. If I have a number multiplied in front, okay, so remember, if it's a number in front or outside the bracket, it would be something vertical. So this is a vertical stretch by 2, because it's a big number. It's going to stretch that graph out. If I put the 2 multiplied inside the bracket, then this is a horizontal stretch. It's actually not a stretch at all though, right? Because a big number actually means it's compressed by 1 over 2. So compressed in half. A to the x, so that whole function, I add this value. Well, this is something being done outside the bracket. This is a vertical shift or translation up 2. This is a horizontal shift. Remember, plus 2 you would think would be to the right, but it's reversed, so it's left 2. So you already are experts on transformations. You don't have to spend too much time worrying about them for this function. The next thing we want to do is talk about, like we did with quadratics, we want to talk about how we solve equations. In this case, how do we solve exponential equations? So things that involve an exponent and an equal sign, where the unknown or the variable is in the exponent. And unlike linear quadratic equations, these can be really tricky. That's why we have a whole chapter dedicated to solving equations. There is one trick though. If I have an exponential equation, so it has an equal sign and an unknown in the exponent, if the bases on either side of the equal sign are the same, then I can set the exponents equal to each other. So in this case, for this statement to be true, x minus 1 is equal to 5x. Just going to put a note, because the the bases are equal, we can set the exponents. Since the bases are the same, we can set the exponents as equal. Oof. Now I can easily solve this, so I bring 5x to the other side, or I'm going to have negative 1, subtract x from this side, so I get 4x. So I get x is equal to negative 1/4. Do you believe me? Maybe not. Let me check. When I do a check, I look at the left side and the right side. Left side is going to be 3 to the negative half minus 1. That gives me 3 to the negative 1/4 minus 4 over 4. That gives me 3 to the negative 5 over 4. On the right side, I have 3 to the 5 times negative 1 over 4. That gives me 3 to the negative 5 over 4. So they're equal. So I'd say left side equals right side, check mark or something like that. Here's another question. Again, this is an exponential equation because it has an equal sign and there's an unknown in the exponent. How do I solve it? Well, unfortunately, 5 and 25 are not the same base. However, I know that 25 is 5 squared. So let me rewrite this. Now I can equate the exponents. And now I have a solution. X is equal to negative 2. So solving exponential equations is possible using this nifty trick when the bases are the same. Let's do a word problem now. Facebook. We have a function that gives us the number of users based on the number of months after Facebook was born in 2004. So X is the number of months after Facebook started, N is the number of users in millions. So if I sub in a number of months, I'm going to find out how many users they have. When did Facebook obtain its billionth user? So I'm going to find the 1 billionth user. So that would be 1,000, that would be million, that would be billionth user. So I'm going to sub in N is, okay, so N is the users in millions. So I'm going to cross out, so basically I want to find when N is equal to 1,000, right? N is equal to 1,000, that's how many users in million. 1,000 millions gives you a billion. Okay, so let me sub that into this equation. So I have 1,000 equals 1.32, 1.1 to the power of x. Okay, well, I need to solve for x. One thing I can do, I know that these are multiplied together, so I could divide both sides by 1.32. I could do BEDMAS backwards here. I'm going to need my calculator. So 1,000 divided by 1.32, that gives me, oh, made a mistake. 1,000 divided by 1.32, that gives me 757.576 equals 1.1 to the power of x. Okay, so now I have a problem. I want to figure out what x is. I had a strategy to do it up here, but it only works if I can make the bases the same. And I have no idea how to make 1.1 to the power of what gives me 757. So there's a few issues here. There's a few possibilities for solving. The first one you could do is do guess and check. And that's actually what I teach in grade 11. I say just, if you get a question like this, you can just try different numbers. So you could try 1.1 to the power of 8. Okay. 1.1 to the power of 100. Okay, that's much too much. So it's 1.1 to the power of 80. 2,000, 1.1 to the power of 70. Getting pretty close. So you could do it by guess and check. Second method you could do is you could say 1.1 to the power of what gives you 1.1 to the power of x. We cannot easily equate the bases. We need logarithms, which is in this chapter. So we are going to learn the method to solve this, which we will learn once we know logarithms. So this is kind of a question we will return to be continued, because I don't know how to solve this without logarithms. Maybe you learned, but we're going to see the backstory of logarithms, so we will come back to it. And there actually is a third way. And you guys are IB students. You have a graphing calculator at your disposal. So you could graph with the GDC. You could graph the two functions here. So you could graph y equals 1.1 to the power of x and y equals 757.576 to find the point of intersection. If you think about this, so here I'll do a quick sketch first. Okay. If you think about this in terms of being two graphs, think about solving a linear system of equations. You graph this and find where they're equal. 1.1 to the power of x is some sort of exponential growth, so it's going to look something like this. And y equals 757 is just going to be some sort of horizontal line up here. I don't know where. Y equals 757.576. So we want to find out what this is. I can do that with my GDC. Let me just grab a GDC. Okay, gotta delete everything here. So I'm going to graph, you see this, 1.1 to the power of x. So that's my first function. Oh, there it is. It's a very gentle exponential. I'm going to graph as well. I forget how to do it. Tab. I got to grab 757.576. Ooh, don't see anything. That's because I'm not zoomed out. Let me zoom. Fit maybe might work. Oh. Nope. Menu. Window zoom. Don't worry if you don't know how this works. I'm going to teach you. Let's do a Y max of 800 and a Y min of 0. So I'm just going to set my parameters. Interesting. Okay. Menu. View. Window zoom. How embarrassing. The X value is going to go from 0 to 100, say. Let's do that. Ah, there it is. Okay. So there's my exponential. There is my flat line. I need to find the intersection point. Menu, analyze graph. Don't worry, I'm going to teach you how to do this. That intersection point is 69. POI is 69.6, comma 758. So therefore, X equals around 70 months. So in 70 months, Facebook got was a billion users. Of course, who uses Facebook anymore? Okay, your homework is, that's it. Sorry, that's it for exponential functions. Really, we're ready now to move on to the unknown, which is logarithms. Our homework, though, to make sure we're comfortable with this, is page 114, number 1, page 108, number 1 to 3, plus the natural, oh boy, I can't see anything. The natural exponential activity, which is part of this lesson. This lesson continues with an X investigation here, the natural exponential function. Most of this, I've worked hard to make it so you can go through this on your own. And this is going to teach us a little math term that we should know. You should be able to get up to pretty much this box on your own. I recommend you try on your own, and then you can come back and revisit the video where I'll explain it. So if you want, do your homework, pause the video here, and then go try this investigation on your own. Okay, welcome back from pausing the video. Let's look at this investigation. So hopefully you've done this already. I'll try to go through it quickly. Let's say you invest $1,000 in a bank account. It doubles that amount every year, which is 100% interest, which is impossible. But let's just imagine that you have a really good interest rate. Does anyone know what interest rates are right now? Coronavirus, right now, they are 1.5% interest. So you really wouldn't get a lot of interest right now. But anyways, 100% interest. So you have 1,000, 100%. So effectively, your money doubles. At the end of 1 year, you have $2,000. That's an amazing bank account. Now, what if instead of what if the money's paid out more frequently? So instead of getting 100% interest at December 31st, what if you get 50% of the interest at the end of June, and then 50% of the interest at the end of December? Under this new payment structure, calculate the following, and just do this like by thinking. You don't necessarily have to worry about formulas. So how much money is in the account at the end of the first payout? Well, you would have gotten 50%, so you would have at that point $1,500. Over the second half of the year, you earn interest on the bank account balance that you calculate in Part A. How much would you have on December 31st? So remember, to get this amount, I had to do 1,000, and I multiplied it by 50%. That gave me 500 interest. Right, so in this case, I have $1,500 in my account. I multiply that by 50%. And I get $750 interest. $750 plus what I originally had in my bank account gives me $2,250. This is the idea of compounding interest, interest on interest. Here I just earned interest once. Here I earned interest at the end of June, so now I have more money in my bank account. So I earn more interest in the second half of the year, and I actually end up with more in my account. So if you had a choice between the two, interest once a year or interest twice, well, I would obviously choose twice per year, because I get more cash. What if I were to continue this trend? So instead of compounding interest twice a year, what if I did it 4 times a year, every month, every week, every day? What do you think would happen? The total amount seems to increase. This seems like a great deal. If I just collect interest more often, I'll have more and more money in my bank account. So we're going to look at this. So I've started your table for you. You have number of compounding periods per year. So in 1 year, if you compound once per year, you're taking $1,000, multiplying it by 1 plus 1. So multiplying it by 2, you get 2,000. If you compound twice per year, like we just showed, you're going to take 1,000, multiply by 1 plus 1 over 2 squared. I can count. This should be exactly what I just did. Don't worry about this formula. Like, we just gave it to you, but this is essentially what we did in question 2. So I have 1 plus 0.5, so 1.5 to the power of 2, and then I multiply that by 1,000. So that's how I got 2250. If I did it 3 times, you could figure it out, or you could just use the formula now. So 1 plus 1 divided by 3 to the power of 3 times 1,000. So that gives me 2370.37. And we can continue. I'll pause and I'll finish filling this in for you. I wanted you to look at the multiplier, which is how did your money grow? So I have 2,000 divided by what I started with, my money doubled. In this case, I have 2250 divided by 1,000. So my money went up by 2.25 times. Here I have 2370.37 divided by 1,000. This gives me 2.37 times. So it does seem like I'm getting more. Here I have doubled my money. Here I have 2.25 times. It doesn't go up quite as much, but it's still more money to have my money compounded 3 times per year. So I'm just going to pause here and fill the rest of this in for you. Okay, we're back, and look, everything's been filled in. So I've followed the pattern here of dividing by the number of compounding periods. Hopefully you weren't tricked. It doesn't keep going up linearly. I do start doing some larger values. So here, I mean, think about this. This is compounding 10,000 times per year. So there's 365 days in a year. So you're compounding several times per day. So this is very impractical, but this is just a theoretical idea. So we see that the account balance keeps going up. And when I look at the factor, it keeps going up too. But look carefully. I went from 2 to 2.5, that's a big jump. Then to 2.37, it's a bit smaller, not as big a jump. And actually, as I compound more and more, my multiplier, and actually the amount in my account, starts to level out. And I reach this multiplier, 2.72. I've gone from 1,000 to 10,000, and the multiplier is essentially the same. So, look at my findings. What happens to the multiplier as the number of compounding periods becomes very large? It reaches 2.72. Or more formally, as the number of compounding periods approaches infinity, that is, as this number gets bigger and bigger and bigger, my multiplier approaches 2.72. This is important. Doesn't just increase forever. It reaches this number, 2.72. what is this number? Well, we give it a special name. It's called Euler's number. And we actually call it E. It's on your calculator. Mine is there. It's over top of the lawn. To access it, I need yellow. So second lawn, E1, there it is. 2.71828. 2.71828, etc. This is one of those amazing numbers. It's like pi. It's like the golden ratio. It's an irrational number, so it continues forever. And it has a special, it's so important it has its own kind of letter. But it is, the E stands for Euler, which you spell like this, who's the mathematician who kind of is credited with this. This number, where did it come from again? It comes from the idea of doubling your money very, very frequently. So compounding very, very frequently. If you do that, you reach Euler's number. We define the natural exponential function as an exponential function of e to the power of x. So in this case, 2.72 to the power of x. It's going to look like this, just like any other exponential function. This is 0, 1. There's an asymptote. So this is just an exponential function, but it's special because it's the natural exponential function. I tried to explain it here. What does E mean? Is the growth when something is being compounded infinitely frequently. Imagine you work at a bank where you put coins into a bank vault every time the interest compounds. So if you had an infinite number of compounding periods, or like 1,000,000 compounding periods, you'd essentially be going into this bank account, putting in little bits of interest every second of the day. That if you did something like that, the growth would follow this exponential curve. So what would it be like? You would be putting interest in the account every second or less. I know it's a very abstract idea. This is the kind of best explanation of this number. You're going to see a lot of E in the IB questions. E is just a number. E just means 2.72. You can Google it. You can use your calculator. Don't be overwhelmed by E. Just replace it with 2.72. Right? I can write y equals e to the x, or y equals 2.72 to the x. It's just like pi. When you see pi, you have been programmed to know this is 3.14. And just a final question, just as a thinker, we've only calculated the bank account balance for 1 year. What if we were to have the same with this same compounding per year, how much money would we have after 6 years? So year 1, you'd have 1,000 times E. That would be year 1. Then you'd have times E again. So this would be year 1. This would be year 2, etc., etc. So you'd have 1,000 times e to the power of 6. Type that into my calculator. 1,000 times shift e 6. That's how it works on my calculator. And I would have, wow, tons of cash all in my bank account. 403,428.79. Again, this is a pretty magical bank account where you double your money every year, more than double your money every year. So it's very much impossible, but at least you get the idea of how we're able to figure that out. So that's the explanation of E. You're going to see a lot of E in the coming year. This is where it comes back from, this idea of compounding very frequently. Just to link it to real life, when we have a mortgage for our house, you can choose to pay interest every month. You can choose to pay interest every year. It's a different amount of interest, right? If you pay your mortgage every month, you actually end up paying a little bit more to reduce the principal faster. Whereas if you were to just pay your mortgage once a year, you would actually pay a bit less. So I hope that doesn't confuse anyone, but the compounding period does affect your savings a little bit. Okay, so good luck with the rest of the homework, and we'll see you next time.